So let's show a utility system to understand how this actually occurs. Here's a typical power utility system involving multiple phases and a neutral. Our concern is not about the phases. We only show one picture, one line here, but there could be 1, 2, 3 phases up here, as well as the utility's neutral. You'll see that the utility neutral is grounded, indicated by the green wire and the ground rods. And the utility's neutral gets grounded every pole or every several poles, and this is just for safety and to reference the neutral to earth, again for safety, and it's just part of a multi-grounded system. Now we'll add a little additional feature. If we had a voltage gradient present for this scenario, the voltage gradient as shown from right to left would cause current pickup on the right, flow down the utility neutral, and discharge on the left, again following this established system. Further, there's other connections that, if the gradient is present, can also have current flow on them. You'll note that I've added in the lower left that there's a phone company bond. Typically, phone companies tie their sheath and their equipment to the utility's neutral because they're in such close proximity in the right-of-way. Also, up at the transformer, you'll see that customers served with power have a grounded neutral that goes to, in this case, the residence on the right and the rectifier on the left. Two different services, same transformer. They each have a neutral, but it's continuous and metallic, and in the presence of that gradient, current that could get picked up at a house could flow on the utility neutral to the transformer neutral bushing, and then further flow down to the rectifier on the left. So this is another view of those various currents that are picked up and discharged. There's in red the current pickup at the distribution power neutral, flow down the neutral wire, discharge off of the neutral ground at the pole, and the guy anchor. In blue, I'm showing pickup at the house, flow down the house distribution neutral, the customer neutral, and then because of the bond at the transformer, that can also flow further down to the rectifier and discharge off of the rectifier stand. There is a phone company bond. I'm not calling that a ground. I'm going to refer to that as a bond, but because it's tied into the utility neutral, current flow discharges off of that phone pedestal. And also because of the bond at the transformer, the original current picked up on the utility's distribution system in red really also flows to all these same points as well, and I'm showing that with a red arrow discharging off of the rectifier stand. Back at the rectifier and phone company pedestal, this is what the scenario was. So from the upper right, the rectifier or pipeline neutral coming in serves the load at that rectifier. We show it coming into a power panel. The neutral is tied to ground. The ground is tied to the support structure, and that's the path by which interference current, because of the voltage gradient, could flow down this neutral through all these structures and discharge off of the rectifier stand, which then subsequently fell over. The phone company bond is somewhat similar. A bond to the utility neutral ties to the metal frame of the phone company's pedestal, and then because it's in that same electrolyte, it can discharge off of there to the pipeline.